Many students, when they first start learning calculus rigorously, often hit a wall at the precise definition of limit, which is epsilon-delta argument. Usually, when we think of limits, we imagine something like fx approaches L as x approaches C. If we draw it, it seems very intuitive. According to the Wikipedia, in mathematics, a limit is a value that a function approaches as the argument approaches some value. But it sounds like a repeated explanation. When we are only dealing with one-dimensional real-valued functions, it feels like we can always just look at the graph. Then we say in plain words, as x gets close to C, fx gets close to L. But how can we turn this intuition into rigorous mathematical language? It's not too difficult. We just need to translate the ideas of as x gets closer and fx gets closer to L into precise mathematical terms. So what does get arbitrarily close mean in mathematics? Let's say we have our reference point C. Then we pick some arbitrary point x. Now imagine an alien comes along and challenges. Here's very small number epsilon. Can you make sure that you can find a point x which satisfies the distance between fx and L is smaller than this epsilon? If you can always answer yes, absolutely, then we are proving that fx indeed approaches L. But of course, to make fx approaches L, we need to control how close x is to C. That's where delta comes in. Delta depends on epsilon. The smaller epsilon is, the smaller delta must be. Then we can formally write for every small epsilon, which is positive, there exists a delta such that whenever x minus c is smaller than delta, fx minus L is smaller than epsilon. So it's like the alien gives us epsilon, and we have this function. This is C. So this is L, and this is small epsilon. In this area, for every x here, fx minus L is smaller than epsilon. So this value is delta. Example 1. Limit x when x goes to 0. Sin x is definitely 0. It's very easy, right? This one is sin x. This is very easy, very trivial. And second example is, let us define fx is x when x is not 0. But this is 1 if x equals 0. This function will look like this graph. Then third example. Let's work out explicitly how to find the delta in terms of epsilon for a given function. I choose fx equals 2x squared and c equals 0. We want to find delta in terms of epsilon. So when fx is smaller than epsilon, we can observe this result from this condition. This is same as this expression, because what we want to show is this one. Then we can say that for every epsilon, positive epsilon, there exists delta equals, I will choose this is arbitrarily constant to make delta small enough such that whenever x minus c is delta, this is equivalent to this one. It can be trivially calculated from this. Therefore, we prove it. Okay, last example. Let's say then since we have 1 and 2, okay, first fix epsilon. There is delta 1 such that whenever you can be surprised by this too, but we don't have any problem because the definition says that for every small epsilon, this value is arbitrarily small number, so we don't have any problem. We have a similar statement from 2. Then choose delta never Probe. The Epsilon-Delta technique is the foundation for rigorous concepts like continuity and differentiability. So it's essential to really understand this definition. But just because you don't understand something right away doesn't mean you are not good at math or that you're doomed. Some concepts are simply hard to grasp at first. If you don't get it, just memorize it for now and revisit it from time to time to see if it makes more sense today. Eventually, one day, you might truly understand it. Thank you for watching my video.